In this video, we're going to see how we can take any particular vector and then create a vector of length 1 in that same direction, and then use that idea to then make a vector of whatever length we would like to in the direction of the original given vector. And we'll also talk about what's known as IJ notation. So some more notation coming your way. So let's start by finding a vector. Let's find a vector, a unit vector, in the direction of, and we'll call this vector v, and it's going to be given in component form as 3, 5. So what we mean by a unit vector is a vector of length 1. So to create a unit vector, we first need to know what is the magnitude of v. And if you remember, I'm going to change that to make it a little bit nicer. Hold on. I'm going to try to make the numbers work out really nice here. So let me make that 3, 4 instead of 3, 5. Because then the magnitude turns out to be much nicer. It's going to be just a nice even 5. So now to get a unit vector in the direction, now this is Mr. Street made up notation here, but I think it communicates well. So I'm talking about a unit vector, and I'm going to use u. That's not always the case, but I'm going to use u to suggest unit vector. Then I'm going to write a subscript of v to say that I want it in the direction of v. And so what I'm going to do is I'm going to take the original vector v and divide it by its magnitude. And so in our case, that means we're going to get the component 3 divided by the magnitude 5, and then the component 4 divided by its magnitude 5. So this is now a new vector, but the idea is it's a length of 1. So visually, what's happening here is, our original vector 1, 2, 3, 1, 2, 3, 4. Our original vector v was something like this. Now, not a vector of length 1. What we have now done is create a vector u that's pointing in the same direction, but now it has a length of 1. And that's going to be, as we'll see, sometimes useful. Just to convince yourself, this is always going to be the case, but you can convince yourself that the magnitude of u is indeed equal to 1 if you look at the square root of 3/5 squared plus 4/5 squared. That's going to be the square root of 9/25 plus 16/25, and that's the square root of 25/25, which is the square root of 1, which is indeed the case. Okay, so let's practice another one. Let's say P is going to be the point, -1, 4. Q is going to be the point -3, 9. So first, let's find vector PQ, reviewing what we did earlier. So this is going to be tip minus tail. So I'm going to get a -3 minus the -1, and then a 9 minus 4. So that looks like, let's see, -3 plus 1 will be a -2, and then a 9 minus 4 is 5. So there's our vector PQ. Now let's create a unit vector in the direction of PQ. So first what we want to do is find the magnitude of PQ. And this is not going to be so pretty. That's going to be the square root of 4 plus 25. Yuck, that's the square root of 29. So that's going to make our unit vector P. We'll take our original vector PQ and we'll divide it by its magnitude. And similarly, the y component becomes there, and we'll be expected to rationalize that. And hopefully that's not a big deal. And we'll get to -2 square root of 29 over 29, 5 square root of 29 over 29. So there is our unit vector in the direction of PQ. So some new vocabulary and ideas here. So we will say that 1 comma 0 and the vector 0 comma 1 are known as the standard unit vectors. So they are, we'll call them the standard unit vectors. So these are vectors of length 1 that point in the x and y direction. So if there's our xy axis, then this vector right here is going to be a vector of length 1 that's in the direction of the x-axis. And 0, 1 is going to be a vector of length 1 that is in the direction of the y-axis. Now, there's some more notation I'm going to throw at you here. So another way of referring to these vectors is we will sometimes see, we'll use I, and in the book this will often be written as a boldface I, which to indicate that it's the unit vector in the direction of the x-axis. I don't write boldface very well here, so I'm going to put the little vector sign on top of it. So I, this notation, just plain I, represents the vector 1, 0. And J is going to be the same as that standard unit vector in the direction of the y-axis. So what that means is we can sometimes take these vectors that are given in, say, component form. So suppose I said here is our vector v, and in component form, we wrote that earlier as 3, 4. We can write it as what we will say a linear combination of I and j. So you're going to see these directions sometimes. Write the vector as a linear combination of I and j. And so what that means is that you could think of, now you don't have to write these in between steps like I am, but you could say this vector 3, 4 is the same thing as 3 times the vector 0, 1 plus 4 times the vector 0, 1. But we said that the vector 1, 0 we are going to call just I, and the vector 0, 1 we're going to call j. So this notation means exactly the same as this. Okay, they're just two different ways of writing the same thing. And sometimes this notation has certain advantages. Most of those we won't see until probably BC calculus. But do not, this is an abuse of notation, it is not correct. So vector v, it is not correct notation to use the angle brackets and the ij both. That does not make sense. Don't do that. I will count it wrong. So these are interchangeable, but you can't somehow mix them up there. Okay, so let's see if we can do some examples like that. So let's say u is going to be the vector 2, negative 5. And I'll say v is going to be the vector negative 1, 3. So can we write u and v as linear combinations of I and j? And of course we can. So u, it just means we're going to write it as 2i minus 5j. That's it. That's simple. They mean the same thing. And similarly, v will be a negative I plus 3j. Not a very good j. So we can then do arithmetic with these as well. So if we wanted to find, say, 2u minus 3v, And let's also do this in ij notation. The idea is this no longer even looks really much like vectors, although you know what that means, but we're just going to do it like it's an algebra problem. So we're going to go 2 times u, which was this 2i, oops, that was supposed to have been a j back there. Let me fix that now. Hope I didn't confuse you and lose you earlier. So that's 2 times 2i minus 5j, and then a minus 3, and that's going to be a negative I plus 3j. And now we just do this like it's a big algebra problem. So distributing, we'll get 4i minus 10j, and then a plus 3 minus 9j. So combining like terms, oops, I lost the I on that. 4i plus 3i is 7i, and a negative 10j minus 9j is a minus 19j, and that's great. Now that means the same thing as the vector 7 comma negative 19. Those are just different notations for the same vector. Okay, let me come back to this unit vector idea and see how we can use it to create vectors of whatever length we want. So let's say that w is going to be the vector negative 3, negative 4. So let's create a vector, we'll call it just A, that is 10 times the length of w in the direction of w. So the process goes something like this. We're going to first create a unit vector in the direction of w. That is, we're going to create a vector of length 1, and then we're going to come and take that vector and multiply it by 10 to give us a vector of length 10. So remember, to create a unit vector, we first need to come back and find the magnitude of w. Well, this was carefully constructed so that its magnitude comes out nice, 5. So u, this vector, is going to be vector w divided by its magnitude. And so that is going to be a negative 3/5, comma, negative 4/5. So there's our unit vector in the direction of w. So now it's pointing in the right direction. There's our vector. Now we want to make it have a length 10. So what we do is just take 10 times that vector u. And in this carefully constructed problem, that becomes, let's see, 10 times the 5 will cancel. That's going to be a negative 6, comma, negative 8. So there is our vector in the direction of w with a length of 10. All right, let's talk about another idea. We say that 2 vectors are parallel. So this is a new idea. 2 vectors are parallel if they are multiples of each other. So the way we get 2 vectors to be parallel is if they're multiples of each other. So if P is the vector 2, 3, and Q is the vector negative 2, negative 3, the question is, are they parallel? And hopefully it's not too big a leap to say yes, and that's because P is equal to negative 1 times Q. So they are multiples of each other. Now you get a weird thing. There's a strange thing that comes out here because that means the 0 vector is parallel to every vector. I know that's a little disconcerting, but that's just a consequence of the way we have defined parallel with vectors. Because no matter what vector you pick, if you multiply it by 0, you get the 0 vector. So the 0 vector is parallel to every vector. Crazy, crazy. All right, see what you can do with homework 51.